you all know, but some people on YouTube might not know.
Hi, Dima.
Hi.
Hello.
Okay, I think I'm unmuted. Yes.
Okay, so it's my great pleasure to present Birgit Speh from Cornell University and introduce her talk on the decomposition of discrete series representations of affine symmetric spaces of SOPQ when restricted to SOP-1Q.
So this is definitely a talk about work in progress. Due to working at home and all sorts of things, this got very much slowed down, but I want to present it anyway. It's examples and conjectures. So let's move to the topic. So this is really a generalization of the Gauss-Prasad conjectures. And this is exactly why I chose this title, because this is the title pretty much exactly the same for the first paper by Gauss-Prasad. The only difference here really is representations of the discrete of affine symmetric spaces. So that is added in, but the rest is exactly the same title. It's very closely related, basically relating what goes on in these spaces to what goes on for discrete series. And so it is work in progress, and I'm sure that there will be some changes necessary and some adaptations of some indices and so on. So bear with me, because I really did not look through all the possible cases, but I hope it's really of interest to everybody. So this is joint work in progress. Part of it is joint with Toshi Kobayashi, and part of it is joint work with Ben Ørsted. This is sort of complicated because there's a theoretical part and there are lots and lots of computations of putting things, looking at examples. So, and you will see later how things are together, how everything fits together. So the outline is the general setup. Then I move to the conjectures and the examples and the supporting evidence. The main references is, of course, the original paper by Gauss-Prasad. Then there is a recent preprint by Colette Mecler and Renard, Series discrète des espaces symétriques et paquets du Arthur, and that plays an essential role in this. Another essential role, which is played by the paper by Yanis and Akshay, Periods and Harmonic Analysis on Spherical Varieties. Symmetric spaces are, of course, special kinds of spherical varieties, and the connection between this and the discrete series here of the answer packets and so on all goes over this paper by Mecler and Renard. So other references are my joint work with Kobayashi about branching laws and symmetry breaking operators, joint work with Ørsted on period integrals and branching, and in the examples I will also mention joint work by Yoshiki Oshima. Okay, so what are our affine symmetric spaces? They are homogeneous spaces, G mod H, where H is the fixed point set of an involution of G. So we worked with G, SOPQ, and then the affine symmetric spaces are of this form. We take SOPQ and divide it through S or RS times SO P minus RQ minus S. And so G acts, of course, by the left regular representation on L2 of this space. And there lies a discrete spectrum if 2R is smaller than P and 2S is smaller than Q. And these are what I refer to as the representations in the discrete spectrum. And the analysis of this was started a long time ago by Flenstedt-Jensen. And his formulas still play a role here. It was continued by Schlichtkroll, and the final classification of the representations is due to Oshima and Matsuki. So the spectrum here is completely known. And let's start out with a quick review of these representations. And I'm always assuming that I have a regular integral infinitesimal character. So I'm looking at the infinitesimal character of a finite dimensional representation. And for safety's sake, in some of the conjectures, I may even want to have a self-dual finite dimensional representation. Okay. So these representations are all of the form AQ lambda. So they are parametrized by a zeta stable parabolic subgroup Q of G and a unitary character of the Levy of this parabolic. So in this case, the spectrum, the S is, we take S, the space is SOPQ, SOR, S, SO, P minus R, Q minus S. And the Levy in this case is SO20R, SO02S, and SO, P minus 2R, Q minus 2S. So I distinguish here between SO20 and, let's go back, and SO02, just simply knowing how the quadratic form is on these spaces, because this is how the R and the S get in. Okay. So the complexification of the Lie algebra, if you look at it, depends only on R plus S, Lie algebra of L. And there is a Levy subgroup which is associated by Venkatesh and Yanis to the symmetric space. And this is exactly this Levy subgroup. When they talk about a Levy subgroup, this is a Levy subgroup which is associated to this space. And a character is basically a character of the disconnected group, SO, P minus 2Q minus 2S, and characters on these SO2 factors. So Leclerc and Renard shows that for representation in a discrete spectrum, the character of the SO, P minus 2R, Q minus 2S, this large part here of the Levy, is trivial. And hence, all we have to do is we have to look at the character of the torus part here. So that's pretty nice, because then the representations are really parametrized by M integers, which makes sort of life a little bit easier, because we do not have to take sort of constantly look about plus minus, because this is a nice disconnected group, and it just makes life much, much more complicated to think of this. Okay, I went the wrong direction. So there is another thing which Akshay and Yanis introduced, namely, they introduced an L-group for the symmetric space. And the formalism to describe the discrete spectrum of the space, similar to Langland's L packets for the parametrization of the discrete series of a semi-simple group. So homomorphisms of WR, of the Weil group, into this particular L group, and discrete homomorphisms. So what are these? The L group, if we have P plus Q is odd, then it's a symplectic group. And in this case, in the even case, it's an orthogonal group. Yeah, I think that's correct. And this is already the dual group here of the group, and that's why we work over C. So again, this depends only on R plus S. And so, in fact, it depends only on M. And we are looking here at Langland's parameters in this group. That's what parameterizes the representations. Now, this, of course, since I'm working here with the complex group, is not all, well, all the representations are parameterized, but now you run into the trouble of, okay, I have a L parameter. Which representations of my are really represented here? Which of these symmetric groups of symmetric spaces really shows up? All of them are sort of mixed together. Everything where we have R plus S. So now we can talk about these L packets of symmetric spaces, but the next thing is we have to sort of look at a little bit closer of what can we tell. So what I do is I fix an infinitesimal character, L lambda, and I define a Venkatesh-Sakalaridis packet, which I write SV, and then the index P and M, because it depends really on P, Q, and on M. And I take the union of all the representations which appear in the discrete spectrum of all these spaces where R plus S equals M. So if I would like to have the infinitesimal character there also, I'm putting it there, but mostly I'm just working with the package, and I assume I have fixed an infinitesimal character before. So this is basically, well, if we take a parameter, one of our L parameters for the L group of the space, then what we associate to it is really this whole Venkatesh-Sakalaridis packet. So we have discrete Langland's parameters in our L group for the symmetric space. And to each one of these Langland's parameters, we basically assign a element here in, or we assign a packet which lies in SVPQM. So we have a full formalism of L groups for this, except, well, we change the group. Okay. Now, from various computations, it turns out that this definition is pretty crucial. Namely, I care about the M, which if you just look at the representations themselves, you wouldn't really think that this M makes any difference. But I say, I really use the notation about height, that this representation has a height M if it's in PQM. Independent of the P and the Q choice, I pick the M. Now, in the long book with Toshi, we defined height. And it was defined using composition series of our principal series representations. That was the basic idea, looking at composition series, figuring out where and when it appears and when it's a Langlands quotient and so on. So that's where our definition of M comes from. And it plays, if I'm anywhere I'm stating, I would state our branching rules, the M would play a prominent role.
Birgit,
So,
Birgit, is it always non-negative integer, M?
yeah, it's R plus S.
Oh, I thought it's lambda. Okay, my mistake.
No, it's, let's go back. The R plus S is, but M is just R plus S.
Okay, thank you.
So it's always, and I'm not interested in the case where M is equal to 0.
Okay.
I'm interested in, because if M is equal to 0, I'm dealing with finite dimensional representations. Okay. So that's where this idea of fixing the M and looking at the height comes from, because this is an absolutely essential element in formulating branching rules in that one case. Okay. So, as I mentioned, the representations in this, in a packet SMV are parameterized by a representation in the L group, but actually, before I had a GS here, now what Meclair and Renard show is actually that there is an answer packet for this, where all these things live. Which isn't very surprising, because the group, well, the L group with the S at the bottom is really a subgroup of the GL, and so you have a Langlands parameter for that group, and you combine it with the inclusion, and you check what happens, and you get an answer parameter to make everything consistent. Okay. So we now have two things for our representations. We have an answer parameter and we have an L parameter, an L group. So now we need a little bit more. And for the answer parameter, one usually associates some group of connected components of, we look at SV, the centralizer, and the dual group of G, and modulo the connected component. This is a 2 group, and in this case, it's a 2 group of a group set modulo 2 set, and the whole thing to the M. And so we have this group, which we also now have associated to the representations of these symmetric spaces. So we have the full machinery of two things. We have the machinery of L groups. We have to change the group, Langlands parameters and everything. And we have the other parameters here. And so here we have all of these little characters floating. Oops, now I'm moving backward again. So now what you really are interested in is, okay, we have an answer parameter, but the answer parameter determines our whole Venkatesh, or the L group determines everything in the Venkatesh, Venkatesh and Zacharyadis L packet or packet. So let's take one of those, and then what you are really interested in, going backward, having this, and you would like to know in which of these symmetric spaces does this thing actually appear. And here they really determine this, that, well, we have R S equal M, and it depends on this little parameter and this little character, and how often this character on -1 happens to be plus and -1. This is exactly the same kind of conditions you have when you start looking at discrete series for groups. And you would like to know, you have a Langlands parameter, and you would like to know which group in the pure forms, in the Vogel pure forms, would contribute that representation. This is the same idea here, except in this case, we are interested in R and S. If you sort of translate everything back, it comes really down to knowing things about pure forms of, you translate it back and you look at pure forms, pure inner forms of the L group, or which has this parameter M. So those determine precisely which group appears here in this space, which of these spaces appears here. So this is a quite important thing, because then what you really have is, you know your M and you know your R plus R and S, and then you find the space.
So sorry, you mean R and S are 1? They could be, because I mean -1 to the I -1. Is it a +1 or -1?
I here would be 1. So it would be, the I here is the character.
Mm-hmm.
I think the R is
the
supposed to be
value
outside
of
the
the
bracket.
character. I'm writing my.
I think the R is supposed to be outside the bracket.
Yeah.
You're telling how many things in the set it's equal to R. So there's a bracket that's too far to the right. The bracket should go right after the exponent and before the equal sign.
Yes, exactly. You're right.
Okay, so the typo on both lines. So the number of things in the first set is R, and the number of things in the second set is S.
Yes. So the I really, this is a character, the value of your character on these little S, on the little elements EI here. And in fact, of course, you're interested in what happens to -1, because that determines your character. I never care about what this character does on +1. There is 1 anyway. So now that's the background So it's sort of obvious where I would like to go from there. I would like to somehow, if I want to generalize Gauss-Poisson conjectures, I would generalize them exactly to these packets, to the Szekelerides-Venkatesh packets, because a lot of the information I have works for those. And I can tie everything in. So let's recall the branching. So we have two kinds of branching and restrictions. If we have a unitary representation, we may consider unitary restrictions, and everything inside here is unitary. P is unitary, P0, the small representation is P0 is a representation of H0. So everything inside is unitary, and the harms I'm considering here are unitary operators, which preserves the unitary structure. And because I'm interested in here in the subrepresentations, what happens is I can also move, interchange pi 0 and little pi 0 and all pi 0. This is really the interesting part here. We would like to have the small representation as a subrepresentation of the pi 0. Okay, and doing this, we can also look at unitary multiplicities by simply looking at the dimension of these spaces. Then the other concept is smooth branching. So we go to the space of the infinity vectors. We have topology there. It's a Fréchet space. And now every one of these operators is smooth in that topology. It's a Fréchet operator. It's an operator in the category of Fréchet spaces here, no longer unitary. So obviously, this has a good chance of being larger. And so we can consider the smooth multiplicities. Now, it is from examples and from looking at distinguished representations clear that smooth multiplicities and unitary multiplicities are not the same. You often have smooth multiplicities larger. There are cases where the unitary multiplicity is 0, but the smooth multiplicity is non-zero, and so on. So there is a question of in what category are we working at, in the smooth or in the unitary? And what I will do is I will consider here just the restrictions of a Venkatesh package, a representation Venkatesh package, to the group G prime, which is SO P minus 1Q. Now, I have the M here. From looking at plenty of examples, what is suggested is, well, if I take a pi here of height M in the large group, I'm taking a pi of height M in a smaller group, then the multiplicities are the same. Now, this is proved in some special cases. This was proved and really computed. And I will, from now on, since I believe this is correct, leave out the subscripts unitary and infinity in these things. In the examples, I will explain in what cases the examples really use the unitary, and in one cases they use the C infinity. What it means is basically you look at coefficients and you have to estimate the growth of these coefficients. And if you know here your coefficients very explicitly, you get information also here. So you see that they actually really decay faster, decay as fast as you like for the unitary thing. You can estimate the cases. That's how it is done in the most cases, and this is sort of an open problem, but I think that it should be done, doable. It really is not the hardest thing because, well, you have, well, if anytime you start computing for an example, you end up with exactly this. But it's very vital that we have M on both sides, the same M. It is simply not true if I do not have M here. There's no chance. Okay. So what we need is, we always need a discrete spectrum. We need a symmetric space, we need a discrete spectrum. And so that's our assumptions here. And the second assumption is simply that the representations here we are looking at, I will not write this down what the thing is satisfies every time, is I will write it as just, I would think of condition B that the infinitesimal character is the same as the infinitesimal character of an irreducible finite dimensional self-dual representation. Probably this can be, the self-dual can be left off and so on, but let's keep that. So with also some, and there are other things which can probably be improved a little. I mean, I could have the case where we will see in some examples what kind of cases are still covered there. So I'm now summing up all the representations with height M, which are in this packet. And I'm taking here the same. I'm summing up all the representations with the second packet for the smaller group. And the first conjecture is that the multiplicity is smaller or equal to 1, where here I have the whole sum of all the representations in the packet. And here again, I have the sum of all the representations in this packet. I pick lambda, I pick mu, firm, and I will always get the multiplicity smaller than 1. So at most, one pair of representations can appear. So, well, why do I have this smaller equal? Because sometimes, for example, if I take G equal SOP, comma 1, then there are very few representations in the packets. Namely, the only symmetric space I have to look at is an SORS P minus S comma 1. And this is to what I divide. There's only one case. So, okay. in both sides, I have only one representation, and you wouldn't expect that if you vary lambda and mu arbitrarily, that you always would get multiplicity 1. You just need to have a large packet on both sides, a full packet, and not just a little bit. And so this is, I expect that we could get 1 if we have this additional assumption, because that means that our packets on both sides for large group and the small group are equal size, and they are both large. They're not just one element. They're really large, and they are as big as such packets could be. But there is, for this, there is not a lot of evidence. Well, there is some, but, and I will present this, but the evidence is only for m equals 1, which isn't a lot, because it leaves out all the complications. Okay. So the conjecture is, the second one is, again, same assumptions, A and B are satisfied. So we have a discrete spectrum. And now here we have multiplicity 1, unitary multiplicity 1. Then, in fact, and my little pi is a representation of G prime, namely the smaller orthogonal group, then it is, in fact, again, a representation of height m. So again, there are, I will in the examples explain cases where this is true, but the cases are usually either P is 1, Q is 1, or M is 1. One of these things which should show up, come down to a 1. Then the examples work. So it would be nice to have more general examples for this. Well, actually, yeah, I could have a Q equals 1 here. And I could have, if I have Q equals 1, then all my M's are allowed. I don't have to put a limit on the M's. It's always one of these 3 has to be 1, and is going to be 1 in the examples. Either I'm looking at all the groups, and I'm looking just at M equals 1, which turns out to be comparatively easy computations. And then I can do it. But if not, then I really have to start with Q equals 1 or P equals 1. If I want to really give evidence for this. Okay, so even if the second conjecture would be true, we still have a problem, because I tell P is contained in this whole packet. That's one of many, but we would like to know which one is it, which involves knowing R and S. And well, even if we know those, we have to be a little careful, because for that space, there may be several families. So, okay, let's look at this. this is basically the problem. We would like, given the P, capital P, I would like to know what my little p is. So we have the pair. We have capital P, we have little p, and we know we have 1. So this is the only pair which would contribute. So we would like to know which ones are they? Which one, what is this pair? Which is exactly the same problem as comes up if you look at the cross-Poisson conjectures. So to attack this, one can start looking and following the ideas which Benedict Cross and Dipendra had. And there, this little group of this set of characters and the characters on this group of order C2 plays a major role in doing this. And well, we have here the same kind of thing. We have Mecler and Renard and the answer packets, and we know to each element here, which appears in here in SVPQM, there is a nice unique character here assigned. Okay. So what we have to do is, the first step is, given these two representations, if all the conjectures are correct, then this is sort of a unique pair. One is in the large the Venkatesh-Sekularides packet of the large group. The other one is in the Venkatesh-Sekularides packet of the smaller group. And this is a unique pair. So we now can sort of try to follow their lead and relate this to interlacing properties of the parameters or of the infinitesimal characters. Either way should work. So the second step would be to find once we know R and S and R prime and S prime, we need to know all the representations which are in these spaces and know which representation precisely do we pick out in this. Okay. And there was a step 3. Once we have all the predictions, we actually need to show that these conjectures are correct, which we get. So for step 1, we had this group set to the M. For the second group, second case, we had a set to the M also. And well, we can take the same, exactly the same algorithm for going from the interlacing pattern to a character of these two groups of A, groups of sec 2 to the M for the answer packet of phi and the answer packet of phi prime. So it's exactly the same. You write them down, you order them with the interlacing packets, and then you count how many elements are of one type are larger and how many elements of the same type from the other ones are smaller. It's the same, exactly the same algorithm. You work it out. And so, okay, you get a character. It's -1 to some power, and the power is determined for the EI, depends on exactly the interlacing patterns. That was sort of an ingenious idea, that you can go from the interlacing patterns to pair of characters. And now we have the pair of characters. Now we use Mugler's and Renard's result, which I stated before, going from a character to determine R and S, and the He prime determines R prime and S prime. So interlacing patterns using the same algorithm, we get a character on these groups of C2s, and this determines our R and S and R prime and S prime. And so the symmetric spaces. Okay. So now, if we want to be good, we can also sort of, instead of taking parameters, we can add some rows to it. And then in one case, we get half integers. In one case, we get integers. And so, in fact, we can get here, the parameter here would be smaller, or the parameter would be larger. So if we have m equals 1, we have one positive number we have to deal with. Or actually for the large packet, we have 1. For the small packet, we have 1. So we can look if A prime is smaller than A, or if A is smaller than A prime. This produces us this character. And if A is smaller than A prime, we get this character. Okay, where did I go too far? So that's just, so, okay, once we have the characters, we can check what does this mean, going back to the formalism of Mugler, and we see that pi would be in the discrete spectrum of SO p minus 1q, capital pi, and little pi would be also in the discrete spectrum of the same type of symmetric space. Namely, we have here p minus 1, and here we have p minus 2. So m equals 1 usually means we can just forget about the group of symmetric group, as the group here of the C2s. Okay. So in the other case, the theorem of Mugler explains, okay, well, we actually have a representation in the discrete spectrum where we have q minus 1. And p is also in the discrete spectrum of similar space where we have q minus 1. So that shows that we have a fundamental difference here, because our A runs between, A prime would run here between A and 0. And, and here, A prime is larger than A. So all parameters A prime are allowed to be larger than A, which means there are finitely many representations which appear in the restriction. In the first case, there are finitely many representations which appear in the restriction. Here, infinitely many appear. So I will come back to this example when I'm looking at, oops, I'm actually almost out. It should be going fast now. So step 2 is we now have to find the representations which sit there. We have the data R and S, R prime and S. We need to know which representations appear here and, well, first of all, how many families and which ones in these families. And that leaves us very similar thing as in the cross-Brassard conjectures, and we can use again a similar idea. So let's go on. Step 3, well, there are cases which have been done, some special cases, and I expect that some of the techniques can be generalized. Period integrals or symmetry breaking operators or dual reductive pairs. So most of the examples have been computed. Seesaw pairs, most of the examples have been computed, or all of the, well, most. 95% have been computed using some of these techniques. But there's a good chance that some new things are needed. Okay, so quick look at the examples. This is an example which I referred to earlier. It's the example which is a key example in my work with Kobayashi. And let's assume that n is odd because the formulas are sort of different a little. So the representation here is cohomologically induced from a theta stable parabolic subgroup. And here we have SR2, 0, M. So it's a smaller group, Levy is a smaller group of the same type, and here we have the SO2 M. So they have height M. And for any fixed infinitesimal character, with condition B, there's exactly one representation in our packet, our Lenker-Secularides packet for both, in both cases. And so we have everything is parameterized by a sequence of decreasing numbers, and the other one the same. And so we can have an interlacing pattern, which is this. And what we show is if both P and pi satisfy, have this interlacing pattern, then in fact, the dimension here is equal to 1. So the multiplicity is 1 between those representations. And it's completely related to the interlacing pattern. And the pattern here is, well, there are finitely many possibilities for each one of these. So in this case, we get immediately that our conjectures 1 and 2 are correct. There's just not much space to be bad. But this was one of the sort of key examples where it works. The problem here is that it was proved for smooth restrictions and not unitary restrictions. Now, recently there was a thesis by Weiske in Aarhus, and he showed that this also works for unitary restriction. But he picked one infinitesimal character. I did not check all the details if it can be generalized, but I think it can be generalized to the whole case that we have to work. If we have our assumptions, then unitary restriction is equal to smooth restriction in that case. So that's what he shows by simply using estimates on the coefficients. And that should be, there's no reason to assume that his conjecture, his estimates won't work because of the fact that these interlacing conditions really get us smooth stuff. Okay. So now m equals 2, m equals 1, we have to look at these two symmetric spaces. At first glance, you would be thinking they're the same. What is the difference between them? But these things have sort of for a long time caused a lot of confusion. For one thing, I'm now restricting to p minus 1 here, and then things really change. So if we take infinitesimal characters mu and nu, then each one of these packets has to have two representations. And our conjecture here is really true, which I have, namely, I'm picking with same infinitesimal character, a representation p, a representation p minus, and the same for the small group. And we have a unique pair here. Okay, let's check. There's a more detailed version here. So we pick parameters A, B for the representations of the large one, for the small one, C, D, and few assumptions. What happens is we have that this homomorphism is equal to C if C is smaller than A. And if I'm going here to D, a D which is larger than C, then, okay, this is badly written. I should put D larger than C here. Then for nothing larger do I get anything. I type plus here. And the other case here, I am picking now a minus here in the first one for the other space, for the space where I take Q minus 1. And I try to see if this plus D would show up. And, well, it does, but only if D is larger than B, and otherwise I get 0. And this is really done for unitary restriction. The third interesting example goes back to Yoshiki Oshima. This is unpublished work. And what he looks at, he looks representations which appear here in the space where he takes Q minus M. And again, we restrict to P minus 1. And this is one of the cases where it is shown that this restriction is an infinite direct sum of representations. And everything here is unitary because it's an infinite, it is really a direct sum. There's no continuous spectrum. And all the representations which appear also have my SOM. So the M is preserved. And again, we have our integers and we see we have our integers are in one case, half integers in one case. They are integers, and we get again some nice interlacing pattern. And in that case, the B1 of the smaller group, the parameter here, is larger than the A1. So if one works this out with all the details before in what I showed, this is always the one which would automatically show that the representation here appears, and that this B is larger than this here. And that's the only way it can appear. Okay, so the last one, if I'm looking at discrete spectrum here, and I'm restricting things here to SON, which would be, I'm taking P equal to 0, then what I would get is, of course, the formula for the K-types, and all this formula would fit in, except before, when I was working always, I did not allow compact symmetric spaces. So somehow they ought to be fitting into this whole picture as well, because the formulas seem to suggest. But it is not in my formalism so far. Okay, so there's another special case which is important. Namely, this is a surprising one, where I look at SO3, 2, and I look at the symmetric space. Well, in that case, what we get are all the discrete series of G. So we are back actually really in the case of which Dipendra and Benedict were looking at. And so the algorithm in that case obviously is exactly the same as their algorithm. So that's one reason why I was generalizing their algorithm, because this example clearly had to fit into the whole thing. Because this case, their group here is again the group which Venkatesh and Sakaravidis assigned to the symmetric space is the whole SO5C, or well, depends. Yeah, it's in this case, it's an it's an SP. And so we are done now. I'm still done. I'm running over time. Okay. So let's not look at the details. So what is an open problem is, for example, I cannot find in the literature anywhere where anybody takes a representation, an AQ lambda, which would appear in a space like this, where I have SO11, for example. We always had here a compact factor. Then everything is fine, and everything seemed to be working. But if you have these factors, I don't know a simple example, except the one case which I just showed, this one example by Dipendra and Benedict, or actually it goes back to Kudla and Harris, the computations. There are other problems. One could try to generalize this to unitary groups and find similar examples. It's probably, well, you can do it similar. Then, of course, the Gross-Bassat conjectures work for periodic groups as well. So, and the other thing which works as well is Venkatesh and Sakaravidis, their whole stuff also works for periodic groups. So some of the ingredients here work and are running the same. So I hope that there is a way of thinking about this in this context. And if you know, if you computed such things in somewhere in your work in automorphic forms, please send me the information. I couldn't find more than this, but there must be somewhere more people who computed this. So please send me the information or the references. There must be more. So particularly using seesaw pairs, something must have been computed. Okay, so thank you for your patience in listening to this.
Thank you, Birgit, for your talk. Questions, please.
Can I ask a question, Dima?
Of course. Yes, of course.
Birgit?
Yes,
Hello.
yeah.
Is it true that you were looking at the restriction problem from SON to SON minus 1 of AQ lambda?
Yes,
Only AQ lambda.
only AQ lambda.
And the AQ lambda appear in the discrete spectrum of a symmetric space for SON.
Yes,
So which of the two facts is was already known? AQ lambda appear in the discrete spectrum of SOPQ was known.
yes.
That's a well-known fact, or it's something that you did?
No, I used that. That's a well-known fact, the list of things.
Where does it come from?
It goes back to Oshima and Matsuki to probably 83, 84. They give a
AQ lambdas are from 83.
Yeah, they give a whole list of
AQ lambda themselves are from 83.
Yes. There was a,
And there is a paper by.
yes, in the beginning 80s, this was a big problem. Which representations appear? It started out with Flensted-Jensen, but it was clear that Flensted-Jensen did not cover all cases. And so finally, all the other cases which were not covered by Flensted-Jensen's construction were completely done by Oshima and Matsuki.
Okay. And then you have the branching laws for these AQ lambda representations from larger orthogonal group to next large orthogonal group in one less number of variables.
Yes. But I'm
And
careful
these
about
branching,
how I restrict depends.
AQ lambda goes to AQ lambda.
Yes.
Both,
Even that's not clear.
both the representations. Sorry.
Even that's not proved. One of my conjectures would clearly imply that.
That AQ lambda, the only branching that happens is for AQ lambda?
Yes.
Okay, all right. No, that's all. Thank you. Thank you.
Further questions, please.
I suppose there must be cases where you get some discrete part, some continuous part in your
Oh, yeah.
restriction, right? Yeah, I mean, this must be typical, right?
This is a typical case.
Yeah. And so there are probably very few cases where you just only get discrete things.
Yes.
Right?
Yes. And those are well known. Those are the cases which I sort of refer to as Yoshiki.
Right.
Oshima and Toshi sort of worked out all possible cases where this
We
could
get
happen.
only discrete. Yeah, I see.
Yes. That's very rare.
And did you think at all about how any of this might be related to cohomological questions? I mean, once upon a time, we always worried about the special subvariety carrying cohomology classes for the locally symmetric spaces.
Yes.
Have you thought about what the consequences are for this? I mean,
No, I was busy enough
type
trying
theorems and so on.
I think there are consequences.
Yeah.
Exactly
because
like in your work with Harris.
At least I remember in the old things that I did with Michael Harris that, the very first thing you do is you have some vector bundle, which is given by this finite dimensional that you're choosing. And then the first thing you have to worry about is when you restrict that vector bundle, it breaks up into a direct sum of many vector bundles. And I suppose this is exactly where you get this thing going over the packet in the sub thing, right? The coefficients can vary, the mu can vary over the different things. But maybe can you describe this in a geometric way? I mean, I guess what you're saying is what you've written down is the geometric thing if you just translate in terms of vector bundles, right?
Yes, I think this one way of proving things would actually be going this way. Transforming it into a geometric problem and then solving the geometric problem.
Yeah, but I'm just wondering.
But I haven't thought about it.
Yeah, I'm just wondering if you have examples where you can see, because these sort of Lefschetz theorems say when you restrict cohomology to subvarieties, you get it's injective in a certain range, or surjective in a certain range, and so on, where possibly if your results might say something like if you take not only cohomology, but then you take it to be isotypic with respect to the Archimedean, your AQ lambda, so that you'd only take that piece of the cohomology which is isotypic for that capital pi or that little pi, and what you're really describing is a restriction map on cohomology classes, or a possible non-vanishing.
Yes, that's what it should be.
Yeah, okay. It's very interesting. Okay, thanks.
Any further questions? Okay, thank you again. Next week, we will have a talk of Jilin Lu from Minnesota on a local trace formula for the Gunn-Gross-Prasad conjecture for special orthogonal groups. So, a related talk.
Related to today.
Yes, definitely. So, see you all next week.